Welcome to tutorial 19, where we're going to be investigating D-type flip-flops. As you can see from the screen, we are going to be using a 4013 IC. This is a CMOS chip and it is a dual D-type flip-flop, which means it has two D-types inside it. So we have one with their set of pins running along the bottom and the second one running along the top, with the common power pins 14 and 7. I'm going to be wiring mine up just using the bottom set of pins because I only need to use just one D-type. A little bit about the circuit. First of all, we're going to be using a dip switch, as it's called, because it's much easier to use for slider switches here than it is to use the push button switches, because we may have to press them all down at the same time and hold them on whilst taking some results. So we can slide them into position and they will stay latched. So we have pull-down resistors. So with this little arrangement, when we press the switch, in this case slide it up, the input to whichever pin it's going to will go high. When the switch is down, via this pull-down resistor, therefore the input will be low. A little bit about the inputs and outputs here. We have Q1 and NotQ1 are our outputs. We have CL1, which is our clock. We have RST, which is our reset. We have D1, which is our data. And we have set S up the top. So looking at this, we have clock, data, set, reset in that order. So when I wire it up, that's what we'll be using. So, very quickly, best thing to do, as with always, is to label all the pins to make sure that we don't get ourselves confused. So our clock is pin 3, our data is pin 5, our set is pin 6, our Q is pin 1, our NotQ is pin 2, our reset is pin 4, and of course, even though I haven't labelled it on the diagram, because you should automatically do that now, pin 14 goes high and pin 7 goes low. Now there are instructions there as to what should happen when the circuit is working properly, just as a quick check, but actually a much better check here is to actually take our logic probe and make sure that everything is high or low as it should be. So I'm going to turn the power on, and actually it's worth watching here what happens to the outputs. So these are my two outputs. I have Q on the left and I have NotQ on the right. So the red one is Q, the green one is NotQ. When I turn it on, it just so happens here that this NotQ output goes high, but our red Q output is remaining low. So first of all, check we have power coming into the circuit, high and low, and then on our switches, so we have clock, data, set, reset. So I'm going to go on to the first switch, which is currently low. When I slide it up, it goes high, slide it back down, goes low. Second one, low, slide it up, goes high, slide it back down, goes low. Third one, low, slide it up, goes high, and slide it back down is low. And fourth one is low, slide it up, goes high, and slide it back down, goes low. And you'll have noticed the outputs changing there, which may give you some idea of what's likely to happen in this circuit. So first thing we're going to do, looking at our sheet, it tells us that we have different combinations of outputs. And on the first one, we don't care about clock and data. We are just going to put set high and reset low. So I'm going to slide set high and watch what happens. When set is high, Q is high, NotQ is low. Next, I'm going to slide set low and I'm going to slide reset high. And Q has gone low and NotQ has gone high. Next, all of our switches are low, so I slide them all down, and currently 0, 1. Next, we're going to make D data high. Watch what happens. Nothing. Next, we're going to make clock high. So I'm going to slide up switch 1, and you will notice that now Q has gone high and NotQ has gone low. Next, clock is now a low, so I'm going to slide that back down, and D is still high, and we have no change on our output. Next, they are all low again, and we have no change on our output. Next, clock is going to go high. We're on step number 7. And our output has changed. Q has gone low and not Q has gone high. And then finally, I'm going to make data high. And there's no change. So looking at these results, what can we conclude? Well, first of all, what can we conclude about set? Well, here, set is low all the way down, apart from on that first step. And when we put set high, well, I'm going to go back and just do this bit again for you. When I put set high, what happens? Q goes high. And that's exactly what the set does. When set is high, Q goes high. Notice how I use ones and highs. And therefore, not Q is low. And normally, looking at this, you can see that set is normally low. What about reset? Well, you'll notice that reset is a 0 all the way through, apart from that second stage. Let's do that second stage again. And when reset goes high, you will notice that Q goes low. And that's exactly what's supposed to happen. So when Q is high, Q goes low, and not Q has gone high. And normally reset is held low. So both reset and set are held low in normal situations. Now, what about the data? Not necessarily so easy to deduce straight from the table here, but let's have a look. Here we change the data. Here we change data from 0 to 1. Here we change data from 1 to 0. But if you look at the output, here it was a 1, here it is a 1, here it was a 0, here it was a 0. So when we change data, Q doesn't change. But if you look, the next step in here was actually to change the clock. So what we did was to change the clock after we've changed the data. And as the clock went from low to high, the output also changed. So Q changed. Here it went from 0 to 1, and here it went from 1 to 0. And if you look at data, here data went from 0 to 1, 0 to 1. Here data went from 1 to 0, 1 to 0. So in other words, what this is telling us is when the clock rises, in other words, it goes from a 0 to a 1, data goes to Q. In other words, Q becomes whatever the data is when the clock rises from a 0 to a 1. That is called rising edge triggered. So Q follows D when the clock goes from 0 to 1. So about the clock, our conclusion needs to be a rising edge. If you look at the clock going from 1 to 0, which is here, and actually as we go back on ourselves, it didn't make any difference in Q. What about Q? Well, in this case, When Q was high, the LED was on, but Q is a 1 when set is a 1, and Q is a 0 when reset is a 1. And NotQ is obviously the opposite of Q, and that's very important as well. So hopefully that makes you understand how a D-type works. So very quickly, when set is 1, Q is a 1. When reset is 1, Q is a 0. In normal use, both set and reset are held at 0. And you have to connect them to 0, don't let them just float. When the clock rises from 0 to 1, Q becomes the same as D, and NotQ becomes the opposite of Q. Otherwise, both Q and NotQ don't change, regardless of what happens to D, because D will only transfer to Q when the clock changes from 0 to 1. One very quick point, at the moment, once again, set goes high, Q goes high, reset goes high, Q goes low. What happens when we put set and reset high? Set is high, reset is high. And quite clearly, we can't have Q high and not Q high, because not Q is supposed to be the same as Q, the opposite of Q, and therefore we can't have the two output states being the same. This is the end of tutorial 19.